Alright, in this video we're talking about colligative properties. Colligative properties are dependent upon the number of solute particles. In this we're referring to ions. What the solute is doesn't matter, just how many ions or parts there are. So, vapor pressure of a solvent that contains a non-volatile solute is lower than the pure solvent. And this is one of the colligative properties of vapor pressure lowering. So when we add a solute to a solvent, we change its properties, one of those being the vapor pressure, which then affects the boiling temperature. When you take AP chemistry, we'll talk more about vapor pressure. But for this class, just knowing that the more ions you have, or the higher the concentration, okay, the lower the pressure is. Okay, and this term non-volatile means that the solvent does not easily vaporize. Okay, so it takes a good bit of energy for it to vaporize it, but when you add the solute to it, that lowers how much energy it takes to do that. The two, though, colligative properties we're going to be focused on are freezing point depression and boiling point elevation. So freezing point depression is the difference between the freezing points of the pure solvent and one of the non-electrolyte solution. And so in that solvent that we put into that solvent, so when we put a solute in the solvent, it changes its freezing point. And we can determine by how much, because we have figured out that it is directly proportional to the mole concentration, which gives us the equation you see here. So the change in the temperature, the freezing point, is equal to Kf, which is a constant value, and we don't need this negative here. It's a constant value. 1.86 is for water, and that does change if we change the solvent, okay, times the molality. So if they're directly proportional, if the mole concentration is high, then the freezing point depression is also high, which means that the freezing point is lower. Okay, if we have a high depression, we are dropping the freezing point. Okay, so to find the freezing point, we take the freezing point of the solvent, which in this case, this is the freezing point for water, 0, and we subtract the change in the temperature that we calculate. Boiling point elevation works in the very same way. The difference is that it's elevation, and so this increases the boiling point of the solvent. Okay, so the boiling point goes up with the mole concentration. Alright, so we give the same equation. The delta TB equals KB, which is also a constant value, which would be given to you, and does change if we change the solvent. Okay, times the mole concentration. Now the normal boiling point of water is 100. Again, that's the boiling point for water, right? And so for finding the new one, we would just add our change to that 100. Alright, so let's do some problems. So what's the freezing point of water if we have 17.1 grams of sucrose and 200 grams of water? So again, the TBF is equal to the Kf, which is that constant, times the molality. So to find that change in temperature, we take our Kf, which was 1.86, times our molality. Well, they didn't tell us the molality, but they gave us enough information to find the molality. Right, so we change our grams of sucrose into moles. 1 mole of sucrose, and we add these all together, and we get 12 times 12.01 plus 1.008 times 22 plus 11 times 16 for oxygen, and we get 342.296 grams. And so we divide 17.1 by that molar mass, and we find that it is 0.04995. I can have 3 significant figures, so 0.04 no, 0.0500 moles. Okay, that gives me my 3 significant figures there. Alright, so now we're going to plug that into our molality equation. 0.0500 moles divided by kilograms of solvent. So my solvent, though, is 200 grams, which is 0.2 kilograms. And so our molality comes out to be 0.25, but we only get one significant figure because we only had one significant figure there, so it becomes 0.3. So I plug that in to my change in temperature equation. So I take my 0.3 times 1.86, and we find that the freezing point is going to change by a 0.6 degrees Celsius, again that one significant figure. And so the new freezing point would be 0 minus, because it's depression, 0.6, so we get a negative 0.6 degrees Celsius as our new freezing point. Okay. Let's look at another problem. Excuse me. A water solution containing an unknown quantity of a molecular solute is found to have a boiling point of 100.23 degrees Celsius. What's the mole concentration? Alright, so again, our delta T, in this case B, because we're talking about boiling point, is equal to 0.51, right, because it is a water solution, times our molality. And they just want us to find the mole concentration. So we're just looking for the molality, which means we must know what delta TB is. So what's the normal boiling point of water? That's 100. So if we take our 100.23 for our solution minus what water usually is, we get a change of 0.23. And that goes in as our delta TB. So 0.23 equals 0.51 times the molality. And so we solve then for molality. 0.23 divided by 0.51, and we get that the molality is 0.45. Again, little m for molality. Alright, you worked the practice problem, so I'm going to show you the answers so you can make sure you get them right. So practice problem 1 is 100.12, and practice problem number 2 is 0.175. Okay, and if you have problems getting those answers, you can certainly ask about those in class tomorrow. Okay, next we're going to look at the molar mass. Okay, I want you to ignore this equation for now, and let's just look at how we might solve the molar mass. So, in order to determine the molar mass of sulfur, 1.8 grams of sulfur is dissolved in 100 grams of naphthalene. So this is our solvent, and this is our solute. Okay. And it tells us that naphthalene has a Kf of 6.9, and the freezing point was depressed by 0.48 degrees Celsius. So it went down by 0.48 degrees Celsius. So that's our delta Tf equals our Kf times our molality. So 0.48 is how much it dropped by, and that's equal to our 6.9 times our molality. So we can find the molality by dividing 0.48 divided by 6.9, and we get two significant figures what we're allowed, so 0.070 is our molality. Now let's remember, what does molality mean? That's the number of moles of our solute, so that's our sulfur, over kilograms of our solvent. So we, in this case, it's for 1 kilogram. But how many kilograms do we have? We have 100 grams, so that's 0.1 kilograms, right? And so how many moles are actually in this solution? So 0.07 times 0.1 gives us 0.0070 moles of our sulfur. Right, so now how can we find the molar mass? If you remember, that's the number of grams divided by the number of moles. Right? So I know the number of moles in the solution. We just calculated that. They told us the mass right up here. Right? And so what do we get? 1.8 divided by 0.070 And that gives us 257 grams per mole. But now, how many significant figures are we allowed to keep? Right? This should have just been the one for the one there. Sorry about that. So just the one gives us 300 grams per mole. Right? So that's how we can find the molar mass. Alright, there are 2 practice problems that I want you to do. The answer to practice problem 3 is 32.1 grams per mole. Practice problem 4 is missing information. The Kb for the acetic acid is 55. And then the answer to practice problem 4 is 1100 grams per mole. Again, if you have trouble getting those, we can talk about them at the beginning of class when we meet again.